All right, so in the last couple of videos we were talking about using the ideas of multivariable integration to calculate physical quantities. In this video I want to do a very particular case of that that's really important for dealing with interactions. And that has to do with sort of the idea of using integration to translate distributed forces into effective forces or equivalent forces. Okay? So that's sort of the idea that we're trying to get at here. Now, conceptually, remember that when we talk about distributed forces, what we're thinking about is, let's say I've got some object, and that object is sitting in a gravitational field. I could think about that object as basically consisting of lots and lots of little particles, right? About a mole of little particles, right? So about 10 to the 23 little particles, and each one of those little particles has an interaction with the Earth. Right? There's this large mass of the Earth, and so there's this interaction between this particle and the Earth. So if I sort of go through here and draw all of the arrows to represent all of those forces, there are a bunch of arrows, they're little arrows, but still there are all of these forces acting on every single particle in the system. Right? So if I want to translate that into an equivalent force, what I need to do is ask the question, what's the total amount of interaction that's crossing the boundary into this object, right? In other words, what's the total force? And so if I want to figure that out, conceptually what I'm going to do is integrate over the domain of the object, and what I'm doing is adding up little differential bits of force. Right? Now this is going to look a little bit different from what we've done so far. In the last couple of videos we were talking about integrating scalar quantities. I'm now talking about integrating a vector quantity over the domain, but conceptually all I'm doing is I'm actually just taking all of these vectors and adding them together. Okay, so if I take that one step further and think about this, maybe this is a cube, right? So then I would actually say I'm going to integrate over the domain of the cube, and I'd ask the question, what's the force per unit volume times dV, right? So I'd ask the question, what's the force per unit volume acting on each little chunk of that? So let's do that as a sort of stupid example for this, for a cube in a gravitational field. So here's my stupid example. Okay. So just to define some geometry for this stupid example, we've got x, y, and z. My cube is sitting on the origin and is length L on each side. Okay, so, all right, how do I think about that? Well, I want to integrate over this domain, right? And that domain I could write very explicitly as a triple integral from 0 to L, 0 to L, 0 to L of x, y, and z. Okay, so I'm going to have a dz over here, a dy, and a dx. Okay. I'm then going to ask the question, what's the differential bit of force, or in other words, what's the force per unit volume acting here? And that force per unit volume I could think of as basically being the density of the material, right? So this is the density of whatever this cube is made of, right? Times the gravitational constant. The gravitational force is acting in the negative k hat direction. So the density, the mass density is going to give me kilograms per meter cubed. Gravitational acceleration is going to give me, I'm going to end up getting newtons per meter cubed, so I get newtons per meter cubed times meters cubed, right? And so this ought to integrate out to actually give me a force. If I go ahead and do that integral, let's go ahead and do that. Well, and this for the sake of showing how you deal with these unit vectors inside of the integral, k hat is a constant, so I can pull that out. G is a constant, I can pull that out. Rho is a constant, I can pull that out. And so I end up getting minus rho times G times k hat, triple integral from 0 to L, 0 to L, 0 to L of dx, dy, dz. Notice I've changed the order of integration, but that doesn't matter because all of the integrals are the same. And so in this case, when I do this integral, well, the integral from 0 to L of dx is L. The integral of 0 to y of L dy is L squared. The integral of 0 to L of L squared dz is L cubed. So I get minus rho times G times L cubed times k hat. In other words, the equivalent force is minus rho L cubed times g times k hat. In other words, it's minus mg k hat. Not very surprising, right? That is to say, the gravitational force is simply the mass of the cube times g acting in the downward direction. Okay, so that's kind of a stupid example. Let's do a more interesting example that actually starts to get at what's interesting about this. So we're again going to think about a cube, because cubes are sort of simpler to think about than more complicated shapes. So here's my cube. But this cube I'm going to submerge in water. So I'm submerging it in water just until, so the surface, the top level of the cube is right at the water surface. Okay? And I'm interested in asking the question, what is the total force acting on one side of this cube due to water pressure? Okay? And so if I think about that, let's think about I'm just going to think about this face, right? And I'll draw that face side on. Well, water pressure actually varies as a function of height, right? The deeper you go in the water, the more pressure you get. In fact, the depth of the water, if the water depth is z, the pressure is rho times g times z, right? This has, notice, units of newtons per meter squared. So as I go deeper, the pressure increases, and the reason it increases is that as I go deeper, I need more and more pressure to sort of hold up the column of water that's above me. So I think about this face of the cube, right? When I look close to the top, there's virtually no water pressure at the top, right? At the very surface, there's zero water pressure. But as I go further and further down, the water pressure increases, right? So there's more pressure on the bottom of this cube than on the top of the cube, just as when you get in a swimming pool, your ears don't start to feel pressure until you go deeper. That's because the water pressure is greater as you get deeper. And so now if I want to calculate what the total force was on that face, what I'd have to do is integrate over the domain of that face the force per unit area. Well, the force per unit area is going to be whatever the pressure is as a function of depth, right? And let's define my coordinate system here. So let's say this is z, and this is, let's see, y crossed into z gives me x, so that's x and that's y. No, that's not right. Yes, that is right. So I'm going to integrate from z from across this face, right? This face has differential elements of dy and dz. The direction of the force is always going to be in the plus I hat direction, right? So my differential force, in other words, of one little chunk of this is going to be the pressure times I hat times dy times dz, right? That's the amount of force being applied to one little chunk. That force is in the positive I hat direction. It depends on how high the pressure is and depends on what the area of the chunk is, right? So if I go ahead and do that integral, what do I get? Well, I need to write this sort of relatively compact notation out more explicitly. So I'll integrate from z equals 0 to L, and from y equals 0 to L, rho times g times z times I hat dy dz. And when I integrate this, pretty clearly the first integral, and I should swap these two, the first integral is going to give me rho times g times L squared on 2, right? The second integral is going to pick up another factor of L. So if I actually do this integral, I will get rho times g times L cubed divided by 2 in the I hat direction. Okay? In other words, the force, the sort of effective force acting on this face is not what the mass of the object is. It's actually half of the mass of the object. And you can sort of think about why that is, or not actually the mass of the object, but half of the displaced mass of the water. The reason for that is that as you go deeper, the pressure gets to be higher and higher. Notice one thing I should have highlighted here, this density is the density of the water, right? Because the water pressure is due to that density of the water. Okay. So that's sort of an example of doing one of these integrals of a differential vector element. Notice that you could actually go further and do this for all 5 faces of the cube, right? We could say, okay, well, the equivalent force is going to be equal to the integral over face 1. So let's call that d1 df plus the integral over d2 df all the way up to the integral over d5 df, where if I think about the cube, and here's my cube, so this might be face 1, 2, 3, 4, and 5, right? Now when I go ahead and do this, you can actually see that over face 1, right, my pressure increases as I go deeper, and I get a positive force in the I-hat direction. Face 3, my pressure increases as I go deeper. I'm getting an equal and opposite force in the I-hat direction from face 3. So d1, the force due to d1, cancels the force due to d3, right? Similarly, the force due to d2 cancels the force due to d4, right? So this face cancels the force on that face, cancels the force on that face, the force on this face cancels the force on this face, and I'm left with just the force on this 5th face. Well, the force on the 5th face is actually going to be a constant. There's going to be a constant pressure at that point. So on the 5th face, the force on d5 will end up being rho times L cubed times, what's my coordinate system, k hat, with a negative sign, right? It's going to be pushing up, and since I define z as being down, times g. And I'll leave it to you to go through and demonstrate that that's the case, but it's that same type of idea of integrating over this area and asking what's the force per unit area and in what direction does that force point.